So in the last class, we were talking about the valence band and the conduction band as we know, the valence band is fully occupied with the energy level by electron, and the most important thing is that the energy, and not energy, the temperature level state should be the 0 Kelvin, and for the conduction band, that is meaning that fully empty energy level at 0 Kelvin. So is staying with the temperature state. And if we move on to the relationship with valence band and conduction band, so valence band should be on the bottom and the conduction band should be on the top. So there's between them there's like energy band gap, but between this energy gap there should be certain energy gap, as I said. And if as I told you in the valence band, there's a lot of fully occupied with the electron, but if that electron get the energy, which is excitement energy, that electron move into the conduction band, and in valence band, the place where the electron was positioned, there should be left with a hole. We call it hole. So, but as we know, if one electron move into conduction band, then one hole was made. So call it like it was a generation, heat exchange generation. And sometimes if the electrons, after a certain time, the electron can go down into the hole, which is in the valence band, it means recombination. And if in this between valence band and the conduction band, if certain energy, not certain energy, I mean if the electron field was in this kind of energy level, there is a current flow, and between the current flow we start to talk about in current it's matter with the velocity of electron, and also is important is that the concentration of the electron. So between talking about the current flow, we start to divide into two, but before that we start to talk about the insulator and the semiconductor and metal, which is that the band gap is really big in insulator, and which is really hard to move electron from valence band to conduction band. It's really hard to move on. And as we know, for the second place, we use semiconductor, and semiconductor is like valence band. It's much better than the insulator, but it's not. If we can't compare with the metal. And in the metal, we should think about the free electron and the metallic founding we should think of. And so if we move on to this, because we are talking about the current flow in we are talking about the current flow, and we are focusing on the concentration of the electron and the velocity of the electron. But we focused on the velocity, so we divide the meaning of the velocity into two. So one is the velocity at a certain point, which is called phase velocity, and the second one is that if we look at the one as a one function, we're talking about this function as a group. So we were making definition about a certain velocity called wave velocity, which is the velocity of this certain wave. Not certain wave, I mean the group wave of the velocity. So the phase velocity was defined in the energy, but the really interesting thing is that group velocity was described in the derivative of energy by K. So to get an electron velocity, we should go on to the energy equation. which is really related with Schrödinger equation before we learned. And so we get the result of that the effective mass was related with the curvedness of the EK diagram. So because the mass is matter with the velocity, because as you know, the certain things of the mass is really light, not heavy. It's much faster than the thing with the with the much more bigger mass. So we talk about this kind of thing, and then next we start to look at the EK diagram, which is silicon and germanium and other thing, but it tells a different thing. But we talk about the EK diagram, and as we talk about it, we were looking at the definition of the conduction band and the balance scan. We look at the definition, and it can be changed by the direction we see. And as we keep talk about this, we start to talk about just in-strict semiconductor. So in-strict semiconductor is that, as we know, this is a semiconductor with, like, for example, it's related with silicon. And for in-strict semiconductor, we are talking about that how many holes and electron can be into this kind of semiconductor. And I remember that silicon should be the 10 20. I don't know how to call it in mathematic or like language, but like 10 and 20. And as we talk about this in strict constant semiconductor, we move on to the like n-type and p-type. So but the one thing we can be confused is that the n-type and p-type. So n-type is from the fifth, like fifth one, like the fifth one, like, yeah, fifth one atom number, and that kind of atom has a positive level. So people can think that this is like a p-type because it's related to positive or negative. So but it's unfortunately this whole semiconductor is actually neutralized because that certain atom has a ionized into positive, but unfortunately in the other side there's a free electron in the free electron that is in it. So it means that the whole semiconductor is neutralized into neutralized. And so if I go look at the certain type of the semiconductor, I start to look at the thing that is left behind. So n-type is left to it, a free electron, and the p-type is left with a hole. So it's kind of, hole is not positive, but it's kind of related to the positive value. So I start to remember like that. And that, like, if anyway in strict semiconductor is filled with the silicon, like that kind of certain atom, but if the other type of atom came into it, we call it doping. And there's like that kind of atom we call donor and acceptor. So it's different by the type we are, the type, which type is in semiconductor. And next, if I describe about the thing, that we start to talk about the Ohm's law really shortly, about the between the current density, which is related with the electron concentration, and the other part is related with the photon velocity, which is this. If I just combine these two into it, we can find out that a certain current is going like that. So, and if we know, and then in the next part we talk about the Hall effect. So Hall is different with Hall. We are talking about the semiconductor, and Hall is the name of person. So and about the Hall effect, we can know the polarity of it, and as we know, we are focusing on the velocity before we are talking about, and we should focus on the concentration. We should know about the concentration about certain value of the polarity. So, and next we talk about the density state, which is related with the probability of the like it's like a in classroom professor said it's really like the seat that should be in. So I'll talk about more next time about the Hall effect and the density of state.